Triboluminescence is a fascinating phenomenon where light is emitted when materials undergo mechanical stress such as rubbing, crushing, or fracturing. The term combines the Greek word tribein, to rub, and Latin lumen, light. The light originates from complex processes involving charge redistribution, electrostatics, and quantum mechanics, making it an area of active research in material science and physics. Crushing sugar crystals or snapping adhesive tape in the dark produces visible flashes of light, showcasing triboluminescence in everyday materials. It's like striking a match, but instead of a flame, the friction generates photons as the material reorganizes at the molecular level. When a crystal structure fractures, it disrupts the equilibrium of charges within the lattice. This creates localized regions of positive and negative charges, generating a strong electric field. Electrons in the material are accelerated by this field to higher energy states. When these electrons relax to their ground states, they release the excess energy as photons, producing visible light. The electric sparks seen when breaking apart adhesive tapes in a vacuum demonstrate charge separation and recombination under mechanical stress. It's like pulling apart Velcro. The force disrupts the bonds, analogous to lattice charges, releasing stored energy in the form of light instead of sound. In piezoelectric crystals, mechanical stress induces an electrical charge due to the displacement of ions in the lattice. This localized electric field can ionize nearby molecules or excite electronic states, which then release light as they return to equilibrium. Quartz and some organic materials exhibit this effect prominently. Cracking quartz under stress generates faint light due to the piezoelectric effect. This behavior is also exploited in lighters, where mechanical force generates a spark. It's like squeezing an orange to release juice. The applied force extracts something hidden, in this case, electric charges that result in light.
When the electric field generated by stress in the material is strong enough, it ionizes surrounding air molecules, forming a plasma. The ionization of nitrogen and oxygen in the air produces characteristic violet and blue light. This process is further enhanced if the material contains fluorescent compounds, which re-emit absorbed ultraviolet light at longer wavelengths. Crushing wintergreen lifesavers in the dark produces a blue glow as the sugar crystals ionize the air and the methyl salicylate fluoresces under ultraviolet light. Analogy: it's like lightning in a thunderstorm, where a strong electric field ionizes the air, producing plasma and visible light. Impurities in a crystal's lattice influence the intensity and color of emitted light. Rare earth dopants, such as europium in fluorides, exhibit triboluminescence with specific colors due to their well-defined electronic transitions. These materials emit light by following specific energy pathways dictated by the impurity's electronic structure. Europium-doped materials emit bright red or green light when stressed, providing insights into how impurities alter electronic behavior in crystalline structures. Analogy: it's like adding spices to food. A small addition dramatically changes the flavor, or in this case, the emitted light. Triboluminescence serves as a diagnostic tool for understanding fracture mechanics. Observing the light emitted during crack propagation reveals stress distribution and energy dissipation in materials, aiding in the study of structural integrity. Triboluminescent materials embedded in structures can provide visual cues about stress accumulation and potential failure points. Analogy: it's like using a thermometer to measure temperature changes in real time, but here, light reveals stress distribution. Triboluminescence simulates high-energy events such as meteorite impacts, offering insights into the physics of collisions. The light emitted helps quantify energy transfer and material response during such high-impact scenarios. Simulated meteorite collisions in labs with triboluminescent materials mimic the energy dynamics of planetary impacts. Analogy: it's like creating a miniature explosion in a lab to study how a full-scale explosion would behave. In certain materials, triboluminescence is linked to quantum phenomena such as charge transfer excitons, where electrons move between molecular sites under stress. This behavior offers a window into quantum mechanics and electron redistribution under mechanical forces.
Triboluminescent materials are being explored for energy harvesting devices that convert mechanical stress into electrical or optical signals. These systems could power sensors or provide real-time diagnostics in environments where electrical energy is scarce. Smart triboluminescent coatings on bridges or airplanes could emit light when under excessive stress, warning of structural issues. It's like installing a pressure-sensitive flashlight that turns on when squeezed, providing immediate feedback. Despite advances, the detailed quantum and molecular mechanisms underlying triboluminescence remain partially understood. Questions include how stress redistributes charges at the atomic scale and the precise conditions for transitioning from charge separation to photon emission. These gaps challenge researchers to integrate quantum mechanics, materials science, and photophysics for a comprehensive model. Why certain materials exhibit bright triboluminescence while structurally similar ones do not remains an open question. It's like knowing a recipe's ingredients, but not fully understanding why some batches taste better than others. Triboluminescence is uncommon because its occurrence depends on precise material properties, such as lattice structure, symmetry, and electronic transitions. The interplay between mechanical stress, charge redistribution, and photon emission requires exact conditions rarely found in natural materials. Many transparent crystals like calcite don't exhibit triboluminescence, likely due to their symmetrical lattice structure, which doesn't favor charge separation under stress. It's like trying to create a perfect rainbow, requiring specific angles, light intensity, and atmospheric conditions. Triboluminescence represents a fascinating interplay of mechanical forces, quantum effects, and photophysics. By studying this phenomenon, researchers uncover insights into material properties, fracture dynamics, and energy transfer mechanisms. Its potential applications in diagnostics, sensing, and energy harvesting make it a valuable tool for advancing science and engineering. Future innovations could leverage triboluminescent coatings for real-time stress monitoring in aerospace and civil engineering. Triboluminescence is like a natural light show, revealing the beauty and complexity of physics through a simple mechanical act.